All right, good morning, everybody. In case you haven't noticed, there is an assignment out. It's due next Wednesday or Thursday. I don't remember which. I think it's next Wednesday. You should try to get it in on time, even though you do have the, everybody has the universal extension or the universal accommodation. So you do have extra time to do it, but you should try to get it in. Assignment 2 appears like 1 minute after the due date of assignment 1. And it continues. It continues from the end of your assignment 1. It continues from the end of your assignment 1. So you'll build on top of your existing solution to complete the game of life. And you'll try out some fun board configurations and see what you can do with the game of life. All right, today's lecture, and probably a little bit into the next lecture, is floating point. So we have to tell you, well, every computing student needs to know how are floating point numbers represented on the computer. And so that's what this lecture is supposed to do. So float and double, these are Java's floating point types. Right? Now remember, every primitive type in Java occupies a fixed and finite amount of memory. Right? And so what does that mean? There's only a finite number of floats and doubles. Right? But you know there's an infinite number of real numbers. So there's no possible way for us to represent every real number using float and double. And in fact, you can't even represent simple numbers like 0.1 or 0.3 correctly. So for example, if you compute 0.1 plus 0.1 plus 0.1, right? Everybody here knows it's 0.3, right? But if you ask the computer, is the value of x the same as 0.3, right? It'll tell you no, right? And you don't have to believe me. You just run it in Eclipse or in your in Jupyter Notebook. So on the next slide, you'll see the following program. So here I've got x, right? Here I've got EQ, right? Is x equal to 0.3? And then here I print the result, right? So if I run that, you get the following, right? The first thing that the program prints out is false, right? The sum of 0.1, 0.1, and 0.1 is not equal to 0.3. Okay, now, what's all this other gobbledygook that I'm printing out here? So there's a class in Java called big decimal, right? We're never going to use it in this course, but it exists, right? So big decimal is arbitrary precision, floating point number, right? So what that means is it gives you the ability to represent a floating point number with as many digits as you want. Okay? It's not the easiest class to use, right? However, if you make a big decimal number and you pass in a double value, which is what I'm doing here, right, you can then ask the object, what is your string representation? Right? So I can pass it the number 0.1, right, and it will tell me what are the actual digits of 0.1 when you convert it to a string. Right? And so when you do that, you get this thing here, right, which is not 0.1. Right? It's 0.1, a whole bunch of zeros, and then some 5s and some other stuff. Right? So that looks a bit weird. So what is that telling you? It's telling you Java can't represent 0.1 exactly. Right? What about 0.2? So what I'm doing here is I'm taking 0.1 plus 0.1 and printing the result. Right? So 0.1 plus 0.1 gives you 0.2, a bunch of zeros, and some other digits. And now 0.1. Oh, I can't do that here. 0.1 plus 0.1 plus 0.1, sorry. Right? That gives you that. Right? At the bottom here, I'm printing out 0.3, right? And that gives you that, right? So now you can really clearly see that, in fact, right, that sum, which is here, is not equal to what Java thinks 0.3 is, right? They are clearly different numbers, right? And if you do 0.1 plus 0.1 plus 0.1 plus 0.1, you get 0.4 and a bit. Strangely enough, if you do 5 0.1s, you actually get 0.5, right? And so that little program there demonstrates conclusively that the Java programming language cannot represent floating point real numbers exactly, right? Even numbers that look simple to us, right? Like 0.1 or 0.2 or 0.3. Now, you have to be a little bit careful with the output that I just showed you, right? So if you actually use a little d double number, right, then when you type in the number, or that value actually only has 15 to 17 significant digits in it when you write it down as a base 10 number. Right? So in other words, once you start to write down more than 17 or 18 or 19 numbers, the extra numbers that you write down are meaningless. Right? Now that program prints out many more than 17 digits. Right? And so what's happening is the computer can't represent 0.1 exactly. When it can, right? So the decimal number is 0.1. The computer converts that to a binary representation of that number. Right? The binary representation of 0.1 does not exist. So you get the closest binary value to 0.1. Right? Now when you ask it to print it out, it converts that closest binary value back to decimal. Right? And that's what it's printing out. Right? So it's printing out that conversion from decimal to binary, and then from binary back to decimal. And that's the value that's getting printed out. Right? So it's not the actual decimal value. Sorry, it's not the decimal value of 0.1. Right? If you actually, you only have 15 to 17 actual digits. Okay, so how are floating point numbers represented on your computer? So it's not just Java that has this issue. It's pretty much every, is it everyone? It's most programming languages. Right? So most programming languages and most of your computers use what's called the IEEE 754 standard for floating point numbers. Right? So by most computers, I mean pretty much any desktop computer that you would buy. Your cell phones probably are all use IEEE 754. Some strange, like some small devices probably don't implement the full 754 standard. I guess some very, very specialized computers may not use it exactly, may not use this particular form of it either. Right? But almost all computers use IEEE 754. Okay. Now, what's in this standard? So the standard is an enormous document. You would need a PhD in, you need a pretty specialized PhD to actually read the document and understand everything that's going on in it. Right? So obviously we're not going to look at everything that's in the standard. What you need to know is the following. Right? That's the important part right here. Right? Every floating point number has the form plus or minus s, where s is an integer value. Right? So s has to be integer, times 2 raised to some exponent, and that exponent is also an integer value. Right? The exponent can be negative. Right? So if you need a value that's less than 1, then your exponent is negative. Sorry, where the magnitude of the number is less than 1, right, between 0 and 1, then that exponent there has to be negative. All right, so remember, s is an integer, e is an integer. Right? So why can't you actually represent 0.1? Right? If you plug it into this formula here, well, sorry. Right? So if I plug 0.1 into this formula here, right, you can prove by contradiction that there is no value s and there's no values s and e such that that equation is true. Right? So remember, s is integer, e is integer. In this case, e must be negative because the value on the right-hand side is less than, its magnitude is between 0 and 1. Right? So how do you do this? It's not hard. Right? So we're going to assume, right, we're going to assume there is some s and some e such that this equation is true. Right? So I multiply both sides by 10 to get rid of the decimal. Right? So we get 10 times s times 2 to the e equals 1. Right? Divide both sides by 2 to the e. Right? So I get 1 over 2 to the e. Now remember, e is negative. Right? So I can write 1 over 2 to the e as just 2 times negative e. Right? And now you have that equation down there. Right? So you have 10s equals 2 to the negative negative e, or to the negative e. E is negative. Right? So the right-hand side is just 2 times 2 times 2 e times. Right? Or I guess you multiply 2, well, it's 2 to the e, right? 2 to the absolute value of e. Right? So there's e2s on the right-hand side. What's on the left-hand side? There's a 10, which is 2 times 5. Right? So I've got the prime factorization. Well, I almost have the prime factorization on both sides. Right? But on the left-hand side, there's a 5. There's no 5 on the right-hand side, so there's no way that this equation can be true. Right? The prime factorizations are not equal. Right? Which means there's no way you can actually find a value of s such that this equation is true. Right? That's it. So you can't represent 0.1. Okay, so float and double are 32-bit and 64-bit binary values. right? So float is some combination of 32 zeros and ones, right? And double is some combination of 64 zeros and ones. Now, I don't want to write 32 or 64 zeros and ones on the slide, right? And similarly, I don't want to work in binary either, because there's probably nobody in here who actually can read binary and make sense of it in any reasonable amount of time, right? So I'm going to use base 10 for the rest of this lecture, and I'm also going to use a smaller number of base 10 digits, right? So I'm not going to use 32 and 64. I'm going to use 4, right? That's it. So I have 4-digit numbers, right? So the digits in my numbers, I have 3, right? So my significand, S, is made up of 3 base 10 digits. First digit is not allowed to be 0, right? So I can't have leading zeros in the significand when I write it down, right? So in other words, the significand is between 100 and 999. Right? My 4th digit is used to represent the exponent, right? So remember, it's a value between 0 and 9. I need to get negative exponents if I want to represent a number that's between 0 and 1. So I'm going to subtract the number 5 from the exponent, right? And that gives me an exponent that's between -5 and 4, right? So now I can write down numbers between 0 and 1. Okay, has everybody got that? 4 digits. First digit is never 0, right? Over here, you can just think of the exponent as being between -5 and 4. Okay, so starting from there, you can ask questions like, what's the smallest positive value that you can write down? Right? So what is the smallest positive value that you can write down? Well, the smallest significand is 100. Right? The smallest exponent is -5. So the smallest decimal value is 100 times 10 to the -5, which is just 1 times 10 to the -3, right? Or 0.001. Right? That's the smallest positive value that you can write down. Right? I can't write down any value that's less than 0.001. So what else can you ask? You can ask, okay, so what's the next largest value? Right? Well, the next largest value must be 101 times 10 to the -5. Right? And so when I convert that to decimal, it's 0.00101. Right? I can't represent any value between these two exactly. Right? So I can't write down 0.01005, for example. Right? That representation doesn't exist. Right? Now, what's the difference between these two numbers? Right? So the spacing between adjacent numbers when the exponent is -5 is 0.00001. Or you just change the last digit in the significand by 1 and multiply it by the exponent. Okay? So the spacing between adjacent floating point numbers when the exponent is -5 is 1 times 10 to the -5. Right? Now, if you keep on going, right, so 101, 102, 100, up to 999, right? When you hit 1,000, your exponent changes, right? So when the exponent becomes -4, the smallest number that has an exponent -4 is 0.01, right? And then the next largest number is 0.101. Notice what happens to the spacing. The spacing changes, right? It was 1 times 10 to the -5, right? And now the spacing has changed to 1 times 10 to the -4, right? So not only are there a finite number of floating point numbers, the distance between adjacent floating point numbers changes, right? Which is weird, but that's the way it works. What happens when I go all the way up to the largest exponent? Right? So when the exponent is 4, the smallest value is 100 times 10 to the 4, which is 1 million, right? The next largest number is 101 times 10 to the 4, which is 1,010,000, right? Now look at the spacing between numbers. Right? The spacing between adjacent floating point numbers is 10,000, right? Which now is really strange, right? I can't write down any number between 1 million and 1,010,000, right? The representation doesn't exist. Okay, so the distance between adjacent floating point values changes depending on the magnitude of the number, right? The exponent. So that distance actually has a name, right? It's called the ULP, or the unit in the last place. Right? It's called the unit in the last place because you can tell what the ULP is just by looking at the last digit. It's always 1, times the exponent of the number that you're working with, right? So the ULP here, 1 times 10 to the 4. ULP here is 1 times 10 to the 2. Here it's 1 times 10 to the minus 4, and so on, and so on. Right? If for some reason you actually need to know what an ULP is for a double or a float value, you can ask the math method, right? So math.ULP, and then pass in the floating point number, and you can find out what is the value of an ULP for that floating point number. Right. Okay, any questions so far? This really is the way it works on your computer, right? Except everything's in binary on most computers. Right? There is actually a base 10 standard as well, but I don't think there's any computers that actually implement the base 10 standard. Right? Most of your computers are binary. Okay, so if I've got a number that I want to represent, some real number that I want to write down, right, like pi, right? When I actually type in pi onto the computer and save it in a double, it gets converted to the closest value to pi, right, that the computer can represent. So there must be some error between those two values, right? And so the absolute error is just the difference between the true value, which is x hat, right, and your approximate value, which is x, right? So if I take the difference and take the absolute value, that's called the absolute error. Right? So when I take some number, some floating point number, or some real number, and I write it down and convert it to a double or a float, right, there's probably some error in the conversion. The error is always less than 1/2 an ULP. Right? So the error is always equal to or less than 1/2 an ULP. Right? But that should be obvious. Right? So if you go back to the table here, let's work with when the exponent's 10 to the 4, because that's an easy number to work with. Right? So I can write down 1 million exactly, and I can write down 1,010,000 exactly. Right? What happens if I write down 1,000,001? Right? So if I write down 1,000,001, well, I can't write that down, right? I can't represent it. So what happens? It gets converted to the closest floating point value, which is 1,000,000. Right? So what's the error? Well, it's 1 times 10 to the minus 6 or something like that. Sorry, it's 1 part in a million, right? Which is much less than an ULP, right? 1 ULP here is 10,000, right? So actually the error here is 1. Sorry, it's 1 in 10,000, right? Yes, 1. No, sorry. In this case, it's not 1. It's less than 1 in 10,000. I'm sorry, I'm being a dummy. It's 1 part in a million, right? So if you keep on going, right, up to 1,005,000, right? What's the error? Right? So when I get to 1,005,000, I have to pick which one of these two values I want to choose, right? Because they're both equidistant from 1,005,000. Right? So I can pick either one. The error is 5,000 in 1 million, which is, if you go back to here, 1/2 of an ULP. Right? So in other words, you can any number between these two values is no more than half the distance between those two values, right? Which is equal to 1/2 an ULP. Right? So your conversion from real number to floating point, the error is never bigger than 1/2 an ULP. Okay, so how do you actually compute errors in ULPs, right? Because we're interested in the error. Remember what an ULP is, right? An ULP is the distance between these two numbers here. Right? So if I want to talk about errors in ULPs, I need some way to do this. Right? It's not hard. You just have to remember the rules. Right? So to compute an error in ULPs, right, you take your true value, right, and you write it down using your floating point representation. Right? So I write it down as some 3-digit number times 10 to some exponent. Right? Then I do the same thing with your other value. Right? So the estimated or the approximate or the whatever you want to call it, right? Your other value x, right? But when you do it, right, you don't necessarily use 3 digits, right? You use the same exponent that you used to write down x hat, the true value, right? So you always keep the exponent the same, right? Then you just compute the difference and you take the absolute value and away you go, right? So 1.29 and 1.25. Right? So I write down 1.29 in its floating point representation. Do I have chalk here? Right, so 1.29. Right, so I need to use 3 digits. First digit can't be 0. right? So that's 129 times 10. Right, now you just adjust the exponent so that you get 1.29, right? So it's obviously minus 2. Right? And now you write down your other number, which is 1.25, right? In the same, trying to use the same representation, but, right? So again, using this representation, but make sure you keep the exponent the same, right? So I need to write that down as some number times 10 to the minus 2, right? So that's easy again, right? That's just 125, right? Now you just subtract. So that's 4 times 10 minus 2, right? Which is, right? So what's the error in the last digit? Well, it's 4, right? So that's 4 ops. So it's actually pretty easy to do. You just have to remember the second number, write it down with the same exponent as the first, right? So here's a slightly harder example. Right? 12.1 is 121 times 10 to the minus 1. Right? Now what's 0.5? Well, I have to use the same exponent. Right? So I need to use minus 1 when I write it down. Right? So that's just 5 times 10 to the minus 1. Take the difference. It's now 116. Right? So that's the number of ops of error. Right? Because your exponent here is the same as the exponent for the true value. Right? So that's 116 ops of error, which is large. Relatively large. Okay, so sometimes you can't, so I told you our floating point representation has 3 digits, right? That doesn't apply to the true value when you're computing absolute error, right? So if your true value has lots and lots and lots of digits in it, right? So for example, suppose it's pi, right? Infinite number of digits, right? Then yes, you try to write it down using our floating point representation, right? But you keep all the extra digits. Right? So you don't worry about them for the purposes of calculating, you don't discard them for the purposes of computing error. Right? So you just write them all down. Right? When you write down the second number, make sure the exponent is the same as the first number. Right? Then subtract, and away you go. Right? So subtract these two, I get 3.875603 ops, and that's your error. Any questions so far? All right. There's also this quantity called relative error, which for some purposes is more important. Right? So the relative error is basically the percent error when you consider the true value. Right? So you compute the absolute error, then divide by the true value. Right? So if you're going to compute, if someone asks you to compute the relative error, you forget everything I told you. Right? You just do this all in using real arithmetic. But I'm not going to ask you to compute relative error, right? We're always going to be talking about errors in ops. Okay, so now that we know how to compute error, how do we actually do some arithmetic, right? So how do I add and subtract, right? Okay, so if two floating point values, you want to add two floating point values, those are called operands, right? If they have the same exponent, then it's pretty easy to add them together, right? So you just add together their significands. Right? In other words, you add together the number in front, right? In front of the exponent. So 12.1 plus 63.8, right? So convert both numbers to their floating point representation, right? So 121 times 10 to the minus 1, 638 times 10 to the minus 1. Add them together, 759 times 10 to the minus 1, right? Easy. Same thing for the second example, right? Write down both numbers. Oh, sorry. Write down both values using their floating point representation, sum, or take the difference if you're subtracting. Right? So here I get 951 times 10 to the 2. Now, what happens if your numbers, so when you add two values, right, obviously you can end up with a fourth digit, right? So, right, if I add 50 and 50, I end up with 100, right? I end up with a third digit. So here, if I add 82.1 and 63.8, right, when I apply all the rules, I end up with 1,459 times 10 to the minus 1, right? But that has 4 digits in it, and my floating point representation only has 3 in the significand. So I have to do something here, right? And so what we do here is you round so that you only have 3 digits, right? So I take 1459 and round it to the nearest 10, I guess, nearest unit of 10, right? Which is 1460 times 10 to the minus 1, which is 146. Alternatively, right, just take 1459, times 10 to the minus 1, right? And then change the exponent, right? So that this has 3 digits in it, right? Then you get 145.9 times 10 to the 0, and now round that value to get 146 times 10 to the 0. Alternatively, you can throw away that extra digit, right? So the other way to do this is to say, well, I've only got 3 digits, so when I have 145.9, I throw away the 9, and I get 145 times 10 to the 0. Right? If I add these two values, I get 1751, so there's an extra digit, right? Convert that by multiplying, by increasing the exponent by 1, right? So 175.1, now round to get 175. Right? And there are your 3 digits. Okay, any questions there? Yes?
What if you're subtracting two numbers?
Yep.
You have 3 digits and look at the original, and then you get 2.
We're coming to that. We're coming to that. Yeah?
So if you add digits and you get more than 3 significants, why doesn't it just saturate?
Well, it would. So for floating point arithmetic, it would saturate if the exponent was large enough. But here I have room for the next higher power, right? If you don't have room for the next higher power, that's when you get saturation. Yeah. No one's ever asked that question before. That's good. Anybody else? All right. Okay. Now what happens if they have different exponents, right? So if they have different exponents, then you pick the value with the smaller exponent. You keep the value with the larger exponent, and then you adjust the value with the smaller exponent so that it has the same exponent as the larger one. Right, so here I've got a very large number, right, 4 million, roughly, plus 12.1. Right, so you write down the larger number in its floating point format, or its floating point representation, right, so 432 times 10 to the 4. Now I write the 12.1 also using the exponent 10 to the 4. Right? And now you can see right away there's a problem. Right? I get 000.00121. Right? Now remember, on my computer, I've only got 3 digits in the significand. Right? So what happens when I add these two values? Well, I get 432.00121 times 10 to the 4. Right? Round that value, and you get 432 times 10 to the 4. So what did we just show? What just happened? X plus y is equal to x, where y is not equal to 0. Right? So floating point arithmetic does not follow the rules of actual math. Right? I can add two numbers. Neither value is 0. Right? Both values are positive. And the answer is one of the original 2 numbers. Somebody came up to me at the end of class a couple of lectures ago. They took, I forgot exactly what they did. They took double dot max value and added 1 to it and asked why. They did something. I don't remember exactly what it was they did. But I think they took double max value, added 1 to it, and they asked me why didn't they get positive infinity, right? Because I told you if you go beyond double max value, it saturates to infinity, right? The answer is because when you add a very small value, when you add a small value to a large value, the small value just disappears, right? In the intermediate sum, you can't represent the magnitude of that small number, right? It's way over here, right? Over here, it's way over here, right? Way past the digits that you can actually hold in your floating point number. Okay, so that's weird, right? I think by this point in time, you should all agree that floating point arithmetic is strange. Right? Okay. Oh, wait. Oh, right, here. So notice here, right? If I actually had extra digits somewhere in my CPU, right, then there's a chance that I could actually calculate this number. Well, in this case, you can't. But if you had extra digits, maybe you could get more accurate results, right? Which kind of sort of makes sense, right? And so you might ask, well, why don't we just put extra digits into our CPU, right? So the answer today is we just stick in extra digits on the CPU, right? So on an Intel CPU, I believe it uses 80 bits to compute arithmetic with double, right? Even though double has 64 bits, right? The problem is back when people were working out how to represent floating point numbers, I don't know how many years ago now, probably 60 or 70 years ago, maybe a little bit less, right? It was very, very expensive to add extra bits, or impossible to add extra bits to your computer, right? So if instead of using extra digits, right, what was your choice way back in the day, right? Your choice was throw away all the extra digits, right? So in other words, when I compute this sum here, right, back here I actually kept all the extra digits, right? So I kept all 8. Here, I'm going to throw away everything that I can't keep, right? So everything past the decimal point just disappears, right? And so now you can see when I add these two numbers, I really do get back the first number, right? Even though the second number is not 0. Okay, what happens when I subtract or add, subtract two values, right? Again, without using extra digits, right? If I take 10.5 minus 9.98, now that's not a hard answer to calculate, right? That's not difficult to calculate. Furthermore, both numbers you can easily write down with 3 digits, right? Except for that second one, right? Because I run into this problem where its magnitude is 1 order of magnitude less, right? So when I write down 10.5, I get 105 times 10 to the minus 1. Right? When I write down 9.98, right, I get 99. I have to keep the same exponent, right? So 99.8. Throw away the 8. Right? Now I get 99. Subtract the two values, I get 6 times 10 to the minus 1. Right? Now if I convert that back to its correct floating point format, that's 600 times 10 to the minus 3. Right? If you actually compute the correct value, right? So in other words, it's 0.6. Right? The correct value is 0.52, right? But 0.6 and 0.52, when you write them out in floating point, is 600 and 520 times 10 to the minus 3. Right? Now, how big is that error? That's 80 ULPs of error, right? Which is enormous because the standard says, right, whenever you do basic arithmetic with two floating point numbers, your answer must be within half an ULP of the correct answer. And this is 80 ULPs, right? So we're 160 times too big, right? So we can't do arithmetic this way. Right? So how do we solve the problem? Okay, so let's suppose we can actually have extra digits, right? So now we have to pick how many extra digits do we want. Well, let's use 1. Right? So if you use extra digits, those digits are called guard digits, right? So if I do the same problem, this time I'm allowed to compute the result using 1 extra digit. Right? So in other words, I can keep, there's a bunch of ways you can do this. I'm just going to write an extra digit after the decimal point. You could also rewrite this as a 4-digit significand. It doesn't matter how you do it. Right? So I'm going to just write an extra digit after the decimal point. Right? So now I can keep the 8, which is nice. Right? So now I can compute the intermediate result, which is 5.2 times 10 to the minus 1. Right? It's an intermediate result because I have 4 digits. I need to convert it back to 3. Right? Now when I convert this back to 3 digits, it works. Right? I get the correct answer. It's 520 times 10 to the minus 3. Right? So that's awesome. Looks like problem solved. Not quite. Right? Almost though, but we're not quite there. Okay, so I'm going to try to attempt to solve a similar problem. Right? Still only using 1 guard digit. Right? So 110, 110.0 times 10 to the 0. Right? 8.59. So remember, write it using the same exponent as the other value. So that's 8.5, and now I have a problem. Right? I only get 1 guard digit. Right? It's obvious here that you need, well, it's not obvious that you need 2, right? But I only got 1. So what happens to the 9? Well, the 9 disappears. Right? And you get 8.5 times 10 to the 0. Right? Compute the result, 101.5. Right? I only get 3 digits in the final value, so I have to do something here, so I round to get 102 times 10 to the 0. Right? The correct answer is 101.41, which I hope you can all easily compute. Right? And if you compute the difference between these two, That's 0.59 ULPs of error, right? So slightly too large according to the standard. Turns out you need 2 for this example here. Okay, any questions about guard digits? It's all the same thing, you just add an extra digit. Right? Whoops, sorry. All right, now what about subtracting? So subtraction is weird, right, on the computer. So when you take 2 floating point values and you subtract them, you end up with what's called cancellation or loss of significance, right? Okay, so here I've got 10-digit numbers, right? We call the digit in the front the most significant digit, right? Why is it the most significant digit? Because it's the one that counts the most to the magnitude of the number, right? So that thing there, that's 1 times 10 to the 10, right, if I'm doing my math right. This thing down here, well, let's look at the 9. That's 9 times 10 to the 1, right? So the digit in the front, right, contributes much more to the magnitude of the number than the digit on the right, right? So the leftmost digit is called the most significant digit. The rightmost digit is called the least significant digit, right? If I take these 2 values and subtract them, right, so I start out with a 9 significant digits here, and I start out with 10 significant digits here, right? And I subtract them. The result is a number with 1 significant digit, right? So even though both of my operands had lots and lots of significant digits, the difference only has 1, right? So that's what we call cancellation or loss of significance, right? There's nothing funny happening here, right? It's just the way subtraction works, right? Take 2 numbers, subtract them. Yes, the resulting number is smaller, right? So nothing surprising here, right? Okay. So because the leftmost digits all disappear, right, or they cancel out, right? That's where the name cancellation comes from, right? Now, if your 2 operands have no error, right, then, I mean, this is just the way subtraction works, right? So it's called benign cancellation. The problem is if you're working in floating point, one or both of your numbers almost certainly has some sort of error in it, right? Either the 2 numbers you're subtracting, they either can't be represented exactly, right? Their true values are not can't be represented exactly in floating point, right? Or you computed your second value or the first value, right? And in the process of computing that value, you've accumulated some error in the result. Now things become problematic, right? So catastrophic cancellation occurs when one or both of the operands contain some error, right? So for example, if I want to compute b squared minus 4ac, right? That's the part of the quadratic formula, right? Then when I calculate b squared, there's a chance that the result of b squared is going to have error in it, right? When I compute 4ac, there's also a very significant chance that that result will have error in it, right? So let's compute b squared minus 4ac using real math, right? Arithmetic, right? So we can crunch that out. So 3.34 squared, right? 4 times 1.22 times 2.28, right? You just pull out your calculator, blah, 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 right? And the correct answer is this, right? 0.0292, right? Now so the funny thing about this number, right? So the funny thing about that number there is that you can actually represent that number correctly in our floating point format, right? It's only got 3 digits in it, so I can actually write it down, right? Now what happens if you actually compute this value using floating point? Right? So remember, this was done using real arithmetic, right? So what happens when you try to do this with our floating point format, right? Well, b squared, I know that's 111556, right? I have a problem, right? There's too many digits in that number, and I can only hold 3, right? So I'm assuming no guard digits again, right? Because doing stuff with guard digits complicates things a bit, right? So what do I do with this 111556, right? So you could throw away the 556, right? But I'm going to try to make this as kind as possible to our floating point format, and I'm going to round instead. So I'm going to go to 112 times 10 to the minus 1. Right? 4ac I know is 111264. Right? So again, too many digits, I can only keep 3, so I'll round to get 111 times 10 to the minus 1. Right? So I've got my two results, b squared and 4ac. Right? Both of them contain error. Right? Here I've lost 0.4 something, roughly. Right? Here I've lost 0.264. Right? Now when I subtract them, right, notice that their magnitudes are very similar. So when I subtract them, I end up with 1 times 10 to the minus 1, right? Which is 100 times 10 to the minus 3, right? Now go back and look at the true answer. 292 times 10 to the minus 4, right? None of my digits are correct, right? The 1's not correct, the 0's not correct, the 0's not correct, and the exponent's not correct, right? All 4 digits of my number are wrong, right? What's the error, right? Well, if I compute the error in ULPS, it's 708, which is enormous, right? Remember, every arithmetic calculation is supposed to result in 1/2 an ULP error, right? Here I've done a few, right? I did the b squared, so that's 1. I did 4ac, so that's another 2. Then I subtracted, so that's 4, right? After doing 4 operations, I end up with 708 ULPs of error, which is enormous. Okay, so this is what happens when you subtract two values with approximately equal magnitudes, right? If the two values have any sort of error in them, you might end up in the situation where you have catastrophic cancellation, right? In other words, your final computed value is nowhere near the actual correct value, right? Now, by nowhere near, I mean in terms of ULPs, right? Its actual magnitude is probably going to be close to the correct value. Right? But when you compute the error in terms of ULPs, it's going to be very low. Right? Okay, so every once in a while, it's possible that you're doing some calculation, right? So you have some equation that you're calculating, and you can transform that equation so that the difference, what's the best way to phrase this? So that when you compute the difference, you're no longer subtracting two approximately equal values. Right? So in other words, you can transform the equation into some other form, and that removes the catastrophic cancellation. For those of you who are curious, you can go into that floating point notebook and look at the examples there. You can actually run the examples. Right? So you can run the examples, you can see what happens when you compute it one way. You end up with an answer that's very wrong. Right? If you compute the same result using a different formula, you end up with a value that's much closer to the correct value. Right? But again, you're not going to be asked about this sort of thing on the quizzes or exam. Okay. What happens if I sum a bunch of values? Right? So suppose I have an array of, I don't know, 1 million values, and I need to sum them all. Now, why do I need to sum them all? Well, I might have to take the average, right? Or compute some sort of statistic, right? Average, standard deviation, variance, something like that, right? So I know that every time I do arithmetic with two values, I introduce up to 1/2 an ULP of error, right? So if I repeat an arithmetic operation over and over and over again, right, there's a chance that that error accumulates, right? I have a 1/2 ULP error after the first sum. I have another 1/2 ULP error after the second, and then another one, and then another one, and another one, right? So there's a possibility that the errors all combine, right, to produce a very large error. There's also the possibility that they all cancel one another out, right? So this doesn't always happen, right? But there is a possibility that they sum. Okay, so here's a little program that you can write or run. I should have put this in Eclipse, but I didn't do it, sorry. So I'm going to use float here because, so double's got 64 bits in it, right? So it's pretty hard to do an example where you can, well, it's not that hard, but I mean, it's easier to do an example with float that shows that there's a problem when you add a bunch of values than it is to do with double, right? So here I'm going to make an array, right? It's got 1,001 numbers in it, and I'm going to fill it with 0.1, right? So 0.1, 0.1, 0.1, right? So there's 1,001 of those, right? And if I sum them, right, you can easily compute that sum in your head, right? Is that what I did? 0.1, right? Sorry, I'm going to set the first value to 1 million, right? So I'm going to get rid of that, 1 million, right? So what does that mean? I have 1,000 point ones, right? And I've got 1,000,000, right? So 1,000 times 0.1 equals 100, right? So that sum, which you should all be able to do in your heads, right, is 1,100,000, right? If you ask the computer to do it, right? So I'm going to just write a loop to compute the sum, right, and print out the sum, right? You don't get the right answer, right? You get 1,125,000, right? So I can't even add 1,000 numbers up correctly and get the right sum, right? Okay, so in this particular case, you can fix the problem, right? So in this particular case, if I move that 1,000,000 to the end of the array, right? So 0.1, 0.1, 1,000,000, right? Same problem. I've just moved the million to the end of the list, to the end of the array, right? Now it actually prints out the right value. You actually get 1,100,000, right? So now that actually works. All that I did was switch where the million was in the array, right? So what do I have to do? Okay, so what's going on here? Right? Well, you should be able to figure out what's going on here, right? The first time, right, in the first example here, I start out with a large number and add that to a very small number, well, relatively small number, right? So what happens when you compute the sum? Well, I lose some of the significance that's in this number, right? And now I've got a large number plus 0.1, right? So when I do the sum, I lose part of that 0.1. Right? And then I've got another large number plus 0.1, and this keeps on going over and over and over and over again. Right? So in that case, when you do the sum, the errors do accumulate. What happens here? Right? Well, I add 0.1 and 0.1. They both have the same magnitude. So when I sum them, the error is relatively small. Right? And I keep on going all the way to the end. By the time I get to here, I have a number that's very close to 100. Right? And so when I sum that with 1,000,000, right, now the difference between these two values is much less than the difference between 1,000,000 and 0.1, right? And so it turns out that that sum, you can actually calculate approximately, well, much closer to the true value than in the previous example, right? And so some people will tell you, oops, sorry. So some people will tell you, look, if you have to sum lots and lots of values, right, then you should sort this list or the array of values first, right? Sort them in ascending order. I guess descending order works. No, you should sort them in ascending order, right? And then do the sum, right? Just like we did here, right? So this started in descending order. I sorted it so that it's in ascending order, right? The reason you don't want to do this is because of the following, right? So number one, if someone's giving you a list or an array of numbers and they're asking you to compute the sum, they're probably not expecting you to change their list or array, right? You just want the sum. There's no reason you have to change the order, right? So whoever's calling your method probably is not expecting you to change the ordering of their array or list, right? So that's no good. Number two, you can't sort in faster. The fastest way to sort is O(n) log n for an arbitrary list of values, right? If I sum n values, that should only have complexity O(n), right? I should only have to loop over that array once. Right? If I sort, I have to sort first, then sum, right? So that's no good, right? So it turns out someone actually worked out a way to how to sum these values correctly in O(n) time. The gentleman's name is, his last name is Kahan. I'm pretty sure he was a prof at U of T. He's also one of the people who came up with the IEEE 754 standard, right? And I believe he has a Turing Award, so the highest award in computing science, in part because of his contributions to how to work with floating point numbers on the computer, right? So this lecture, even though it may have seemed very theoretical, it actually has enormous, the stuff you learned here today is important, right? Whether you recognize it or not, right? It's so important they gave somebody an award for this, for figuring out how to do it properly. Right? All right, so that's it for today. Next week, we'll go back to programming.